We're going to take a look at worksheet number 11. We had 9 to 12 due for homework over the weekend. Specifically, we're going to do questions 10 and 12 here today, starting with question number 10. It says an electron is traveling at 6 times 10 to the 5 meters per second. That's a pretty typical speed, right? What do we say that they should be usually? 10 to the 5, 10 to the 6-ish meters per second. It could be less, could be more even. It just can't be greater than 3 times 10 to the 8. This is like right smack in the middle, though, of what's typical. Through a perpendicular magnetic field of 5 times 10 to the negative 1 Tesla. This is important, right? The fact that it's perpendicular. If it said it was parallel, what would we do here? There would be no force. If it was parallel, there would be no force. If it's perpendicular, we know that we're allowed to use A, the hand rule for deflection that we learned last week, and B, the equation that describes the magnetic force on a charged particle, F is equal to QVB. We want to find that magnetic force, and then we want to find the acceleration. Listen, we know when we want to find the acceleration, we got to get the force, and then we use F is equal to m times A. So let's get the force. Which equation do I use to solve for the force here? F is equal to QVB. Good. Magnetic force is equal to QVB. And usually we write that little perpendicular sign there underneath the V, indicating that the charged particle must be moving perpendicular to the field. But if you forget that, that's not the end of the world, as long as you recognize that this equation is only valid when they're perpendicular, okay? So we're looking for that force. Let's get it now. It's an electron, so the charge is 1.6 times 10 to the minus 19 coulombs. The speed of the particle is 6 times 10 to the 5 meters per second, and the magnetic field strength is 5 times 10 to the negative 1, or 0.50 Tesla. When we multiply those three numbers together, we should get 4.8 times 10 to the minus 14. There's my force. And what do we say for acceleration? Whenever we're looking for acceleration in any context, whether it's magnetic force context or electricity or gravitational or whatever the case may be, remember we said the force needs to be with you. And then once the force is with you, you got to be able to use the force. We're going to Jedi training school again, right? The force is with you. All right, what do you do with the force? Okay, find the acceleration with the force. A is equal to F over m. So we're going to say here, it is 4.8 times 10 to the negative 14. We'd use our unrounded number, but I think that is the unrounded number already. Divided by the mass of the electron, which is 9.11 times 10 to the minus 31 kilograms. Somebody said to me when we were going over the answers to these questions earlier that we have such a high acceleration with such a small force because we're dealing with such a small mass, right? We don't have masses smaller than the mass of an electron. This is the smallest mass we got. So of course, it doesn't take much force to cause a big acceleration for that tiny little mass. Okay, we do the division there, and it works out to be 5.27 times 10 to the 16. You could say that would be meters per second squared. What are the other units that you could use for this besides meters per second squared? Newtons per kilogram, but typically we use meters per second squared, right? All right. Can't remember who asked me for that. Is that okay? Whoever it was? Yeah? Okay, the other question we wanted to go over was number 12, which says an alpha particle. I'm going to circle this because I don't know about you guys, but I have this habit of using the charge and the mass of the electron if I don't draw attention to it, just because, probably because that's what we use like more times than not is the electron data. So sometimes when I see a question like this, I just get a little careless and sub in the mass and charge of an electron without even thinking about it, if I don't draw attention to the fact that it's something else other than the electron. Okay, it accelerates at this rate through a magnetic field of this value. What's the initial speed of the alpha particle? It's kind of backwards, isn't it? This time we have the acceleration. Nick, what do you think we're going to do with that acceleration? Okay, and how are you going to do that? Good. F is equal to m times A. The mass of the alpha particle is 6.65 times 10 to the minus 27 kilograms times the acceleration of 8.00 times 10 to the 13 meters per second squared. And that gives us a value of, I don't have that written down here. Who has that? Yeah, Quinn?
5.32 times 10.
Okay, 5.32 times 10 to the negative 13 newtons. Okay, that seems reasonable. We've got a high acceleration, small force, but again, we've got a particle that has a small mass. Not as small as an electron, but still pretty small. All right, there's my force, and then Nick, let's finish this off. What do I do with it now that I have my force? Okay, which equation? Yeah, good. So we're going to say F is equal to QVB. So instead of getting the force by QVB and then solving for A, we've got A, we get the force by F is equal to m times A, and then use QVB to solve for speed. So let's rearrange that now. I get F over Q times B. I divide that by charge is 3.2 times 10 to the minus 19 times the magnetic field of 0.30 Tesla. Now I'm going to do this on my calculator just to make sure that you guys are dividing the denominator correctly here. Here's the correct way. 5.32 times 10 to the minus 13 times, divided by, let's use brackets on the bottom because everything on the bottom has to be multiplied together before I divide. 3.2 times 10 to the minus 19 times 0.3, and the bracket gives me a value of 5.54 times 10 to the 6 meters per second. Is that a reasonable speed? What did we say a few minutes ago the typical speeds are? 10 to the 5, 10 to the 6. Could be a little higher, could be a little bit lower, but these are pretty typical, right? So you certainly get an answer that's in that range of 10 to the 5, 10 to the 6. Doesn't guarantee you're right, but your odds are pretty good that you're right if you get that value. All right? Now, let's go about this and solve it the wrong way, actually. Okay, the way that some of you still sub numbers into your calculator. Let's say in 5.32 times 10 to the negative 13. Hopefully by now all of you are using the EE button for the exponents, okay, because that's what you should be doing if you're not. Let's divide that by 3.2 times 10 to the minus 19, and then let's times that by 0.3. What's the difference? What's the difference with what I just did versus what I did the first time? Cameron?
Well, two things. You put negative 9, and then
Oh, it should be 10 to the negative 19? Okay, so besides that one, besides that one, smart aleck, Cameron.
it's going to just go in order, so it's going to divide and then times.
Yeah, so what I've done in the first one is divide it by the entire denominator. What I've done in the second one is divide it by the first number, and then your calculator kind of does a little calculation in its head, an in-term calculation. 5.32 divided by 3.2 equals, and then it multiplies the whole thing by 0.3. You can see when I do that I get the wrong answer, right? By quite a bit. So be conscious of that. Either calculate that bottom number, get that bottom number, like separate, and then divide it, or use the brackets properly. All right? We're good there? All right, I want to take a quick look at number 10 again that we just went over. Number 10 says calculate the acceleration or the initial acceleration of this electron. You calculated that value. We calculated that value a couple minutes ago when we were going over this to be 5.27 times 10 to the 16 meters per second squared. I'm willing to bet that nobody in this room gave a second thought to that value once you got it. You got that value, you said, okay, good, I got the acceleration. This is how quickly the electron accelerates at. This is how quickly it speeds up at, right? That's not what's happening. There is an acceleration whose value is 5.27 times 10 to the 16 meters per second squared, but it's not an acceleration showing how quickly this electron is speeding up. Let me show you what I mean by that, okay? Let me draw a picture here of a magnetic field represented by these black X's. These X's, by the way, show the magnetic field pointing which way? Into the page, good. Let's say we've got a charged particle that's going to the right. It's moving to the right through that magnetic field. The diagram that I'm going to show you here, guys, is going to have a few arrows on it. We're going to color code it so that blue is going to represent the direction of motion, the velocity of the particle. So right now the particle is moving to the right. Agree? Okay with that? All right, what I want to do right now is find the direction of the force, not the magnitude of the force or the acceleration, but just the direction of the force. We're going to use one of the three hand rules that we've learned to do that. First rule, the wire grasp rule, is out here, because the wire grasp rule only finds for us the magnetic field caused by the moving charge. That's not what we want to find. The coil rule only finds us the polarity of a coil, and clearly that's not what applies here. The hand rule for deflection allows us to find the direction of the force given an external magnetic field. Which one seems to fit the best? The deflection rule, right? The hand rule for deflection. So let's do that. Let's say thumb, left thumb because it's a negative particle, direction of the particle to the right. Fingers are going to be stretched out in the direction of the magnetic field, the external magnetic field, which is into the page. My palm is going to point, don't say down, but toward the bottom of the page, or you could say down the page would work as well, right? So we're going to represent in red the direction of the force. Okay, got it? All right. We solved in question number 10 for the magnitude of the force. Okay, that's the magnitude of that force in red there, F is equal to QVB. We solved for the magnitude of the acceleration, which is just that force divided by the mass. That's how quickly it's speeding up, right? No, because this charged particle doesn't speed up. And the reason it doesn't speed up is because the magnetic force is not in the same direction as the movement. The movement is to the right. If the force was to the right, it would speed up. If the force was to the left, it would slow down. But the force is perpendicular to the way it's moving. So the speed isn't going to actually change. Watch what happens here. We've got a charged particle moving to the right, force down the page. That means the particle is going to start moving somewhere in between, right? It's going to split the difference. Okay, if I asked Austin to stand up and walk towards the right side of the room, but I pushed him towards the back of the room, he'd end up going over there somewhere, right? Kind of in between the way that I was pushing him and the way that he was moving. So let's look at this and say, using the same logic here, we'd say that this electron would end up going down here somewhere. Right? In between the way that it was moving and the way that it was pushed by the magnetic force. Well, now we got an issue though. Now it's going in a different direction, so that means the magnetic force is going to be in a different direction. Let's figure out what direction the magnetic force is in now. Everybody do this again together. Thumb in the direction of the particle, which is kind of gets hard on old men's shoulders here now. Thumb in the direction of the particle, fingers field, palm points like down and to the left. Down and left like this. So that means force is like this. Where's it going to go now? It's going to go down, right? So the particle is going to be moving more like this. Now we say thumb in the direction of the particle, fingers field, palm points to the left. So we'd say magnetic force is this way. Now it's going to go somewhere in between like this. Thumb, fingers, palm points this way. What does this remind you of? It's a circle. Right? It's moving in a circle. Look, if we join the dots like we did back in kindergarten, it looks like a circle, or at least part of a circle. As long as it's in the magnetic field, it's going to be a circle. Now, once it leaves the magnetic field, like all bets are off, right? But that's a whole separate problem. While it's in the magnetic field, it's going in a circle. We can tell that by joining the dots and looking at the shape, but we can also tell by looking at which way the force points. Which way is the force pointing? This is physics 20 now. Which way does the force point when the object goes in a circle, Spencer? Towards the center. What do we call that when the force goes toward the center of the circle?
Centripetal force.
It's a centripetal force. So here's what we're saying. This equation that you learned and used for your 4 homework questions that you had over the weekend, F is equal to QVB, is absolutely valid. It still is. It doesn't change any of the questions you did for homework. But we now have another equation, an additional equation, another tool in the toolbox that we're allowed to use in conjunction with that. We didn't need to use it for any of those homework questions, but in questions coming up, we may or may not need to use it. The new equation will be this. The centripetal force is equal to mv squared over r. Let's go back to question number 10 again for a second. We wanted to find the force. We wanted to find the acceleration. We calculated that acceleration to be 5.27 times 10 to the 16 meters per second squared. What type of acceleration was that? That 5.27 times 10 to the 16 meters per second squared. Yes, uniform acceleration, because it remains the same value of acceleration, but specifically it was a centripetal acceleration, which doesn't cause something to speed up or slow down, but just causes something to go in a circle, right? Good question. Is that formula mv squared over r on your formula sheet? It's actually not. But on your data sheet, you're going to find A is equal to v squared over r, centripetal acceleration, and you're going to find A is equal to F over m, just General Newton's second law. If you set those two equal to each other, then you're going to end up with, and do some rearranging, you're going to end up with F is equal to mv squared over r. So centripetal force is mv squared over r. But yeah, you're going to have to combine a couple, or just remember the equation in order to use that. So both of these equations are now valid. It doesn't change anything that we've done, even though both of them were valid yesterday, just the same as they are tomorrow. Just that yesterday, even though the second one was valid, we just didn't need it. In some of the questions that we'll do going forward, we will need it, and some of them we won't. Some of them will be just like the ones you did yesterday. Some of them will be different and require you to use F is equal to mv squared over r. But here's a rule of thumb. If the question is one of these questions where you got a charged particle in a magnetic field, okay, this first equation is valid, like for sure. So is the second one, for sure, even if it doesn't mention a circle. But if it has a radius, like if the question says what's the radius of the path, or calculate the radius of the path, or here's the radius of the path, then we're probably not going to use this or this. We're probably going to use this, the combination of those two. And if it doesn't mention a radius, we're probably going to use this. It's not actually very often that we use this equation by itself, although it's possible. Usually it's either the one that we already use quite a bit, or it's this one, which is really the combination of it, mv squared over r equals qvb. All right? We'll do an example here. It's on the sheet that I handed out to you last week, example number 3, and that's going to illustrate how exactly we kind of put this mathematically into play here. It says an electron is moving with a speed of 4 times 10 to the 5 meters per second to the right through a magnetic field of magnitude 2.5 times 10 to the negative 2 Tesla directed into the page. To the right, into the page. Parallel, perpendicular, otherwise? To the right, into the page. Those are perpendicular, right? So the stuff that we've learned with equations and hand rules are valid here, right? What's the radius of the path of the electron and which direction will it bend? All right, what's the radius of the path? What do you think, like what's your gut feeling here you're going to do? Fc equals Fm. Most likely, right? At the very least, we know if we try that, we're trying something valid. If it doesn't work, we'll try something else. But we know we're not going to get the wrong answer with that because it's valid. And odds are, because we're looking for radius, it's going to work for me. Probably a 90% chance or higher. All right, so let's do that. Let's set Fc equal to Fm. Let's set mv squared over r equals qvb. I see a little shortcut here. Do you see something I can do to simplify this a little bit? Not really a shortcut, but a simplification. Yeah, we can cross off a v on both sides. V cancels out with one of the v's on the left side. Now, you don't have to do that, right? But it does make things a little bit easier for us sometimes. mv over r equals q times b. And we're solving for r here. So let's take it up by multiplying. Now, how do I take the qb to the other side? Yeah, good. So it becomes R is equal to mv over q times b. It's an electron, so the mass is 9.11 times 10 to the minus 31 times the speed, which is 4 times 10 to the 5. Pretty typical for the speed of a charged particle, right? 10 to the 5, 10 to the 6. Q is 1.6 times 10 to the minus 19. And the magnetic field is 2.5 times 10 to the minus 2. Now you can do this in your calculator. Make sure you use brackets on the bottom here. You can do this on your calculator. But you know what? There's a trick to do this. There's a trick to do this one in your head as well. Okay? Anybody spot this one? Like most times that's not going to happen, right? Most times we get something like this. We're going to have to use our calculator. But does anybody see the little cheat here? What's 2.5 times 1.6? 1.6 times 2 is 3.2. Add another half, or 0.8, and we get 4. 4 cancels it with 4. And we end up with 9.11 times 10 to the minus 31, 26. Negative 26 divided by negative 21 is 9.11 times 10 to the minus 5 meters. You don't like that? Listen, if this is a test, I'd be using my calculator. Like, there's no question about it, right? Sometimes there's value in going through the mental exercise of trying to figure that out. But if these numbers don't work out so perfectly, there's no way we're going to be able to do that in our heads, right? And of course, on a test, even if you can do it in your head, you're gonna double check that on your calculator, right? Mental exercise is good for you, though, right? Just like physical exercises. Okay, good. Look, there's our radius. What's the direction that it's going to bend, up or down? Let's draw it here. Here's my magnetic field that was into the page. Charged particle going to the right. Thumb, fingers in the direction of the external field, palm points down. Yeah. So we'll say the magnetic force is towards the bottom of the page. Or you could say down the page or something of the sort there. Just remember that we tried right away. I think Austin suggested, was it you, Austin, that said we should use this one? Fc equals Fm? Okay. He suggested that right away because we were looking for radius. And that's good. Okay, that's the first thing I want you to think of when you're looking for radius in the context of charged particle in a magnetic field. Automatically think of that. But if you do try that, and you come across that one question out of 20 that just doesn't work for, then what should you do? Try something else. You get two other things that are valid, right? F is equal to QVB by itself, or F is equal to mv squared over r by itself. Okay? 1 out of 20, but sooner or later, who knows? Maybe you hit one of those. Okay? It's okay. This means you've done something that didn't work. Try something else. All right, what I'd like you to do right now, if you have that copied out, is to take a look at worksheet number 12, please. Questions number 1 to 5 on worksheet number 12. All right, taking a look at question number 4 says, what's the kinetic energy in joules and electron volts of an alpha particle that moves through a magnetic field of that strength and follows a circular path of that radius? I don't remember a question before that has asked us for kinetic energy in the context of a magnetic field. So when I look at this question, I may not be like 100% certain when I see it for the first time what to do with it. That's okay. What do you know about this question? You know there's a charged particle moving in a magnetic field. So you know it experiences a force. You know that you can find the value of that force by QVB. Or since it mentions the word radius, we know that we can use Fc equals Fm. What is that going to do for me? I don't know. Or at least we'll pretend that I don't know right now. If I was doing this for the first question, maybe I don't know what it's going to do for me. Let's just do it and see what happens. This is what I try to drum into your thick skulls from time to time, is that you don't have to know how to solve a question when you start it. There is rarely going to be a question, though, where you can't start it. Like, everybody should be able to start this question. Everybody. Yeah, even if you're not sure, like, kinetic energy, what? Where does that come from? Like, do what you know. This, like, other than the kinetic energy, this is the same as question number 3. So do it like you did question number 3. Fc equals Fm. mv squared over r equals qvb. Because the centripetal force equals the magnetic force. V's cancel. Solve for r here. Solve for, well, what's the only thing I don't have? I got m, I got r, I got q, I got b. Let's solve for v. Just because I don't know it. Not because I know what I'm going to do with it, but just because I can. QBR over M. Listen, in 1969, almost 50 years ago, like, America went to the moon. Why? Because they could. Like, why did Columbus and sail the ocean blue, and why did the Vikings come over to North America like almost 1,000 years ago? Because they could. Like, why are we going to do Fc equals Fm? Like, not because we know where we're going. The Vikings didn't know where the heck they were going. We don't know where we're going with this. Why are we going to do it this way? Because we can. And then it's amazing what the Vikings ran into, and it's amazing what we run into after we end up solving for speed here. Sometimes the light bulb goes on, and we figure out what we're going to do with this, right? V is equal to QBR over M. Q, we're talking about an alpha particle, so it's 3.2 times 10 to the minus 19, times B, which is 0.10, times R, which is 0.025, divided by the mass, which is 6.65. Is that right? Times 10 to the minus 27. Now, on my answer sheet, I don't have that number written down. I've got the final answer, but not that number. What is that number for speed? I'm going to guess 10 to the 5, 10 to the 6. Quinn?
1.20 times 10 to the 5.
Okay, pretty reasonable speed, right? Now, we want to find the kinetic energy. Hey, look, we're the Vikings. We made it to Newfoundland. Look what we found. Hey, I can find the kinetic energy now just by saying EK is equal to 1/2 mv squared. So it's 1/2 of 6.65 times 10 to the minus 27 times that speed that we just found. Jacob, what should you not forget to do there? Don't forget to square, right? Okay, when we do that, we get an answer of 4.8. Yeah, I have 4.8 times 10 to the minus 17. What's the unrounded number, though? 4.79? 4.78? 4.812 times 10 to the minus 17 joules, which we would round to 4.8 times 10 to the minus 17 joules. Now, we're looking for that in electron volts as well. On your data sheet, you can see on the far left-hand side, 1 eV is 1.60 times 10 to the minus 19 joules. So we're going to say 1 eV over 1.6 times 10 to the minus 19 joules equals x eV over 4.812 times 10 to the minus 17 joules. See what I'm doing there? EV over joules, EV over joules. Take the 4.8 up, divide by 1.6, and it ends up, I believe, to 2 digits, 3.0 times 10 to the 2 electron volts. Yeah. We're going to round that to 2 digits, though, because if we go back to the original data, right, we've got 2 digits everywhere there. All right? Now, I'm not going to do number 5 for you quite yet. I'm going to give you a little bit more time on that, but I am going to give you a little hint on that, all right? Most of you guys are either 17 or 18. Okay, let's say you're 17. Okay, say you're all 17 for ease of argument here. I'm 45. What's the ratio? I know it's hard to believe. The reason I don't grow a beard in November is not because I can't grow one, but because it's all gray when it comes in. So I know this baby, boyishly handsome face. Might not look like a 45-year-old face, but that's what it is. Anyways. If I wanted to compare, or you wanted to compare my age to your age, how would we do that? We'd find a ratio. Okay, let's look at our imaginary physics thesaurus again, that book that doesn't really exist. If we say I want to compare, what's a word, Kelly, that means the same thing as compare? You said it. Ratio. What's a word that means the same thing as both compare and ratio?
Compare the ratio.
Divide. Right? If you want to compare my age to your age, you divide. And when you do that, 45 divided by 17 is 2.6. So that would mean I'm 2.6 times your age. 2.6 times as old as you are. That's the ratio of my age to your age. That's the best way to compare my age to your age. You want to compare the ratio, you want to compare the radius, not radius of curvature of an electron, that's a typo. Should say the radius of curvature of an electron's path. Because we're not comparing the size of the electron, right? It's the path of the electron to the path of the alpha particle. So what you're going to have to do here is divide. Divide the radius of the electron's path to the radius of the alpha particle's path. Now, that's easier said than done. This is still a challenge question, but at least you've got a starting place now. Okay? Remember that. Compare means two things. Compare means, Kelly? Ratio and divide. Compare means ratio and divide. All right, number 5, the last one that I'm going to do with you for the day says, how does the radius of curvature of an electron's path compared to the radius of curvature of an alpha particle's path moving through the same magnetic field at the same speed? We went through the analogy a few minutes ago. We said if we wanted to find the ratio, or wanted to compare my age to your age, we divide my age by your age. Not the other way around. Okay, if you want to compare my age to your age, teacher to student age, then you're not going to divide student by teacher age. You're going to divide teacher age by student age, right? If I wanted to compare student to teacher, then I would divide student by teacher. So if I want to find the radius of the electron's path to the alpha particle's path, it's going to be RE over R alpha. Now, if we had a number for RE like we know my age, then this would be easy. If we knew the number for RE and R alpha, we just simply divide them on our calculator. Easy, easy. But we don't know those numbers. So what do we got to do? We got to come up with an expression, equation for the radius of the path. And from that, to do that, we're going to go back to what we usually do when we've got a charged particle in a magnetic field and it mentions the word radius. Fc equals Fm. mv squared over r equals qvb. B's cancel. Rearrange this, solve for r, we get mv over q times b. We get that from taking the r up by multiplying, the qb down by dividing, and this is what we end up with. So we're going to say re, that's going to be m electron, speed electron, over charge electron, magnetic field of the in the electron, or that the electron experiences, divided by, well, the same thing for the alpha particle. The mass of the alpha, speed of the alpha, charge of the alpha, and magnetic field of the alpha. Now, that's kind of an ugly looking equation, right? But there are a couple of ways to simplify this, to make it look simpler. Kessler, what do you want to do here? Okay. Yeah, Quinn?
You can cross out both the speed and magnetic field.
Good. How come you can cancel out the speeds? Same speeds, right? And the magnetic field, same reason you can cancel out the magnetic field, because it's the same magnetic field throughout. So that leaves us with me over q equals, or divided by m over q. Let's simplify this a little bit. Divided by m over q, same as multiply by q over m, the reciprocal. So I'm going to do that. me over qe times q alpha over m alpha. Now we know all these numbers. We sub them in. Here, let's actually sub them in here. I wasn't going to do that, but I will. Mass of the electron is 9.11. Charge of the alpha is 3.2 times 10 to the minus 19. Divided by 1.6 times 10 to the minus 19 times 6.65 times 10 to the minus 27. So let's say 9.11 times 10 to the minus 31 times 3.2 times 10 to the minus 19. Anybody spot something that I could have simplified even that with? What could cancel out of that? I just noticed this just now. Yeah, if you made this, if you took this out of it, this would just become 2. Right? Because it's twice that. Does that make sense? Let's continue on what we were doing, though, and assume that we didn't notice that. Okay, if you do notice it, then it makes your life a little bit easier on the calculator, but we can still do it if we didn't notice that. Let's divide it by 1.6 times 10 to the minus 19, and then let's times it inside the brackets by 6.65 times 10 to the minus 27. And we end up getting 2.74, or 2.74 times 10 to the minus 4. So what does that mean? Well, if you divided the teacher's age by the student age, and you got 2.6, then we would say the age of the teacher is 2.6 times the age of the student. Well, if we divide the radius of the electron's path by the alpha particle's path, then we would say the radius of the electron's path is 2.74 times 10 to the negative 4 times the radius of the alpha particle's path. So there's our ratio there. And it looks kind of odd because of that exponent, but it's really no different than 2.6. It's just a number that psychologically is harder to deal with, but it's no different. All right? I saw one person, I don't remember who it was, that had the inverse of this. What is the inverse of 2.7? That had 3649. What's wrong with that? There is something wrong with that, actually. What have you found if you got 3649? You have not found the radius of the electron's path to the alpha particle's path. You found the radius of the alpha particle's path to the electron's path. So that's like saying, I want the ratio of my age to your age. You found the ratio of your age to my age. My age to your age is 2.6. Your age to my age would be like 0.3 or something like that, right? Which is not what we were looking for there.